So welcome everybody. Thank you very much for being in this presentation. Today we have two guests from PG&E, Mr. Robbie James and Mr. Scott Hayes, who are going to talk about utility experience with traveling wave fault locating on lower voltage transmission lines. Could you please have a brief introduction of yourselves before starting the presentation, and then we move on with the presentation. Thank you very much.
Sure. There's actually three of us for PG&E. Ada is working on her master's degree here. She's worked for us for about 10 months. So next month she gets her master's and is out looking for a job, like most of the seniors there. So I'm Scott Hayes. I graduated from Sac State many years ago. I've been at PG&E for almost 35 years, including some summer internships. I was in school. Most of that time has been spent as a protection engineer. I did supervise the protection group for Northern California for several years, and then I went to our hydro generation group and was a supervising engineer there for 5 years, and I came back to protection where I'm currently a principal engineer. I'm active in some industry groups. CIATI is one, and North American Transmission Forum's another, things like that. I was a local IEEE officer for several years early in my career. We have some students. We also have some SMUD employees who are here to see the presentation. Robbie, introduce himself.
Yeah, and I'm Robbie James, work for PG&E, same office as Scott, West Sacramento. Protection engineer. I've been working in protection for about 9 years now. So, and graduated Fresno State.
Do you want to say anything about yourself? I don't know.
Hi, Adewomi Taiwo. Got my undergrad degree from Fresno State. Get my master's degree at Sac State. Have my advisor right here, and I'm working with them for like about 9 months, 10 months now. So can't wait to graduate.
Do you want to slide advancing what I'm talking about?
Or, well, there's that mouse.
Does the mouse link?
I can just go to the next slide for you whenever you.
Or if the mouse works, I can do it.
Yeah, if the mouse works, I'd rather use the mouse. It's pretty
Just the
interactive.
Is it?
Okay,
Yeah.
so it does work.
All right.
Except when you accidentally click the mouse button. So this is PG&E. This is our approximate service area. You notice SMUD's not shaded out because we do serve natural gas in Sacramento County, where SMUD serves electricity. But this is a map of California in our system. We are a very large utility for the U.S. We're also a little unusual in that we're vertically integrated. We still own generation, transmission, and distribution. The more common model across the country has been to split those functions up. So you'll have a GenCo, a transmission company, Transco, and a DISCO, distribution company. That seems to be a more common model. So we've got, I think we're actually at like 5.6 million electric customers or electric meters, but that's a population of about 16 million people. So that's a pretty sizable population that we serve. We are one of the larger utilities in the U.S. Electric distribution lines, 106,000 miles of distribution, 18,000 miles of transmission. We consider transmission 60 kV and above. At PG&E, some utilities, they would call 60 or 69 or 70 kV a sub-transmission or distribution level. So that can change depending on the utility we're at. About 1 million distribution transformers, old top transformers or pad mounted in more urban areas. We own the last operating nuclear generator in California. Is that a good thing or a bad thing? Depends on your perspective. It's pretty cheap and clean power. The fuel is stored on site in casks. We did announce that we will not renew the license. So the last operating nuclear plant in California will be shut down. I think it's 2025 for one reactor and 2026 for the second reactor, something like that. And the reason is mostly cost. As you drive around and live your life, you are bombarded with people trying to sell you solar panels for your rooftop or whatever. PG&E has 400,000 connected solar generators in our system. And that runs from several hundred megawatts for large commercial projects to 5 or 10 or 20 kilowatts on people's rooftops. Most of the numbers are the rooftop EV interconnects. But they are driving utility business in California. And the state has passed laws that say you will be 100% renewable by like 2035 or something, 2045. Several milestones along the way. So that's really driving things in California. And that's the reason that we decided not to renew or extend the license for our new group. We have 67 hydroelectric powerhouses, although we're currently trying to sell some of the smaller ones. That is, I think, the largest privately owned hydro system in the US. Blizzard, which is an automated restoration system on distribution that senses outages and automatically closes and opens switches to transfer load. We've got a pretty extensive system equipped with Blizzard. Most of our meters are smart relays. Being protection engineers, what do we work on? We work on protected relays, so we do a really thorough job of managing those relays as an asset. To look at how many we have, where we have them, how old they are, what models they are, and failure rates, things like that, so that we can try to replace those before they fail instead of after. Let's see, as most of you are probably aware, our company filed for bankruptcy about a month and a half ago. And that was not driven by our profitability or our finances, that was driven by liability due to wildfires in California. So that is the big issue that all of the California utilities right now are working on, is how to reduce the risk of starting wildfires from electrical facilities. Anything that involves energy involves a certain amount of risk. If you have a car with a gasoline engine, you've got a big tank of gasoline in there, which is kind of like driving on top of a bunch of dynamite. If you have an electric car, you've got a battery that in certain accident scenarios can do bad things as well. Natural gas, electricity, it all involves energy, which is a lot of stored potential energy, which can be a risk if something unfortunate happens. So we are spending a lot of our time trying to look at methods to reduce that risk. That's not just at PG&E, that's across all of the utilities. Even SMUD is looking at some things to reduce their risk profile. So that is the unfortunate fires that we had 2017 and 2018, and the fact that the financial markets say, well, what's to prevent another occurrence in 2019 or 2020? That is what led us to file for bankruptcy. That allows us to access funds. Post-bankruptcy filing, we're still doing business as usual. You can't shut the lights off because it's a public health and safety issue. We're still hiring engineers. We're still getting the work. It's definitely a big issue for us. So I am aware that our distribution engineering group, I think they have authorization to hire 4 new entry-level positions with recent college grads. So I encourage you to apply to PG&E's website. So we are going to be doing some hiring. That's just one engineering group within PG&E. I'm not sure what the plans are for all the other engineering groups. So any questions about PG&E? No? Okay. So today we're talking about traveling waves. And because that's not often covered very in-depth in college, Robbie's going to be giving you kind of a primer on traveling wave theory and how it works and how we use it in utility space. Kind of a question, because we have a fair amount of students here. Have you guys had traveling waves as part of your coursework at Sac State? Which class did you guys cover that in? Okay. And I think it was 1 61 when I was here.
Yeah.
And that was a long time ago. I don't remember anything about traveling from that class.
So we do cover that in graduate classes in our.
Okay.
So, but not enough.
And when I was here, Dr. Balachandran taught a class on, I think it was fundamentals of high voltage engineering. And the book didn't talk about Bewley lattice diagrams at all, but he covered it in a lot of depth in the class. So Bewley lattice diagrams are what we use to determine where a fault is using traveling wave theory. And the Bewley lattice diagram basically describes the wave propagation, reflections, and the time of those propagations and reflections to hit a certain points. And it's not a new theory. This guy, Bewley, wrote about it in 1929, 1931, and 1933. But that was pre-computers, pre-microprocessor relays, pre-microprocessors. And so they were mostly looking at what happens if I get a lightning strike on a line. That induces a wave, which then travels down the line, and if it's an open point, it'll reflect that wave back, and you can get up to a doubling of magnitude, which would fail insulation in a transformer, for instance. They started using that to design surge arresters or lightning arresters for transformers, things like that. So traveling wave and fault location has been used for a long time in certain specific applications. Even communication lines, they've used some of that, but they'll come out and they'll connect some temporary portable test equipment, and they'll run different frequencies, and they'll look at the reflected energy from those different frequencies to try to determine how far out a buried telecom line has a fault. So traveling waves move near the speed of light, useful for fault locating, and now for some tripping relays. We are working with one of the leading relay manufacturers, Schweitzer Engineering Laboratories, on a new application for their latest relay, which in some cases they believe can predict a weak spot in your system or predict a fault location before a fault actually happens. And they've got a couple of documented cases, one in Mexico and one in India, where they identified it far enough in advance they were able to actually go out and patrol that area, find trouble, and fix it before they had an actual transmission. So that's pretty promising. It won't prevent or signal all faults with enough time before it happens. But for some fault cases, there's some promise that we may be able to predict and respond before an actual fault occurs. So that's pretty exciting. And so we're going to install some relays to gain data with that method this year. And we just installed our first relay last Friday to capture that kind of data and see if we can make use of that data going forward. So let's see. Been many papers on applying traveling waves or fault location on EHV lines, which is a term for extra high voltage. So like 500 kV, 765 kV lines, 345 kV lines. Those lines tend to be what we call a clean line with no taps, one wire size, similar construction. Fault locating is great on those lines, but those lines don't have as many faults. And traditional impedance-based methods of determining fault location tend to work pretty well. So we'll talk about fault rates at different voltages on transmission lines, and kind of the different topology or different configurations of different voltages. So how fast are traveling waves and overhead lines? 98% of the speed of light. You guys, electrical engineering seniors, right? You learned that electrons actually move through a conductor at a pretty slow rate, but the impulse of that movement is very close to the speed of light. So that signal or energy can transmit down a conductor at 8% of the speed of light, and you can measure that, record that. So to put that in typical perspective, or more common perspective, 663 million miles an hour. It's a lot faster than your car can drive. Or 186 miles in 1 millisecond. Utility engineers put everything in milliseconds perspective because at 60 hertz, one cycle is 16.6 milliseconds. Everything we do is based on number of cycles per millisecond. So That's kind of our frame of reference. We're not computer design engineers looking at printed circuit boards and very fast clock rates. Everything is 60 hertz stuff. So the plot on the left shows how many miles of different transmission voltage levels we have in PG. So 60 and 70 kV, 115 kV, and 230 kV, all roughly similar in miles of those voltages within PG. 500 kV, which is our highest voltage, it's much shorter, longer lines, but there's a lot less of those lines. The second plot on the right tells you the number of faults per 100 miles per year at different voltages. And remember, I told you that the big high voltage clean lines, they're taller towers, better clearance, bigger right of ways, better design and construction. The fault per 100 miles per year is pretty small. It's tiny compared to our 60 and 70 kV. 60 and 70 kV tend to be built on wood poles. They run a lot closer to trees. The wires are closer to the ground. They tend to be closer to roads where you can have power pole accidents, things like that. So they have a much higher rate of faults per year. So again, most of our industry and most of the papers focus on those extra high voltage lines. I don't know, there's kind of a ego thing in the utility industry about the voltage level you work on, which is weird, but it's true. It's like, oh, you work on those lower voltages. I've heard that comment from people before, and it's stupid, but it's there. Kind of an ego thing about the voltages that you have to work on. So they like to focus on the high voltage stuff. Most of the problems, most of the customers are actually fed from those lower voltages. So that's where we wrote this paper, is to focus on those 60 and 70 and 115 lines because it's more customer impact. The traditional methods of fault location are much more complicated and difficult and not as accurate because those lower voltage lines can have 4 or 5 different conductor sizes in one circuit. They can have multiple spacing and configuration above ground or phase-to-phase spacing on the conductors. They often have taps. They often have tap load stations. They can have in-feeds from generators or ground current, zero sequence current coming from those tap transformers because of the way we connect our transformers. So they are not nearly as accurate to do conventional fault location, which is impedance-based methods. So but basically we're recording the I and the B. We know the phase conductor is a certain ohms per mile, and so we use that basic function with some complex add-ons to reduce error to determine typical fault locations. Traveling wave is a whole different way to look at it. It's all based on time of arrival of waves. So part of the reason we were able to do this is we changed our protection standard, and it sounds like from our discussions with the SMUD guys this morning, that they're changing the same relay that we're using, which is a 411L relay model, that as an option, you can enable traveling wave in that relay. So we're not having to buy a whole new relay to do this. All we have to do is enable that option, pay a little extra for that option, and we have traveling wave relays already installed. So with that, I'm going to turn the complex part over to Robbie, because he's the brains of our group.
Okay, so feel free to ask questions, interrupt me as I'm going along if I'm going too fast. I'm just going to go over some of the basics of traveling wave reflection so we can get comfortable with that again, in case we're not really fresh on our electromagnetics course. And what this really is going to focus on is the single-ended method. I'll go over the double-ended traveling wave method. So when you have relays, traveling wave relays on both ends of a line, it's much simpler than the single-ended method, which is what I'm going to spend most of the time talking about. That's where the interesting stuff happens. That's where you really have to actually care about the stuff you learned in electromagnetics. So here's just a simple example. I have a line with a source. We go to source here, switch, we'll call this a breaker, and it's open-ended. And see what we get here. Close the switch, energize the line, you launch traveling waves, right? You launch voltage and current traveling waves flowing down the line. And in all of this presentation, I'm always going to assume that the action happens during this positive voltage half cycle, just so we can keep a same reference going on. If it happened during the negative voltage half cycle, basically you just flip all these quantities, right? So we'll just keep in mind we're always talking about positive voltages, or at least the energization happening on that positive voltage half cycle. And current flow, I'm always going to define as flowing to the right so we can keep it consistent. So with traveling waves, it's easy to confuse two different parameters we're looking at now. We're not just looking at here the direction of current flow, but also the direction of propagation of these traveling waves. When I first showed that switch closing, we showed that the traveling waves are propagating down the line toward the right. It could be the case where you have a current propagating down toward the right, but the current flow is actually flowing to the left. So that would be negative current flow as I'm defining it here. So, and I show that direction by this polarity here. If I show an uptick right there on the voltage, that's positive polarity in voltage, positive polarity in current, and they're traveling toward the right as shown by those arrows. So this first example, it makes sense because we close the switch, we energize the line. Of course, you get a positive voltage impulse traveling down the line, positive voltage half cycle. You get a positive current impulse because we're energizing the line, current is flowing onto the line into that characteristic impedance of the line. And so what happens at this open end? We get a reflection, right? We get a voltage reflection traveling back and a current reflection traveling back. Since this is an open, we know that the condition to satisfy this is that the sum of these currents has to be zero, right? Because there can't be net current flowing in the end once you have these two traveling waves launched. So we know from this basic case of an open, you get a perfect current inversion. So if you had 1 per unit current here, you have -1 per unit current here flowing back. And you get actually a perfect voltage reflection back. So if you had 1 per unit voltage, you have a positive 1 per unit voltage coming back. So just kind of keep that in mind, the case of an open. And we're going to be looking at different types of impedances on the end of a line. And I'll always refer to those as it looks more like an open or it looks more like a short. If it looks more like an open, you're going to get that current inversion. If it looks more like a short, you're going to get the voltage inversion. And so those waveforms travel back to the source. So now what about the case of a shorted end of the line? So we close the switch, launch the same traveling waves. These traveling waves don't know what's down at the end of the line yet, right? They just see the characteristic impedance of the line. It's the same positive voltage, positive current flowing down the line. But now at the end of the line, now this condition we have to satisfy is that the sum of our voltages has to be zero, right? Because we have a short. So we would expect perfect voltage inversion. So they have -1 per unit voltage coming back. And you have a perfect current reflection, so you get positive current coming back. Let's travel back to the source. So those are your two extremes, the short and the open. Again, I'll refer to those. So the different termination types, I'm going to compare to my shorts and opens. Here I'm just showing, this would be our transmission line that we're concerned with. This is the characteristic impedance. You guys remember talking about the characteristic impedance of a line? So we have to look at when we're looking at these, we're treating lines now as transmission line instead of a lump circuit. And I'm putting a termination impedance here. And let's just see what happens as we come across a junction like this, where you have one characteristic impedance changing to another characteristic impedance. And so the formula we find in the textbooks, this is the formula for the voltage reflection coefficient. Remember, that's going to tell you what kind of voltage you expect to get reflected back once it meets this junction point. And so it's this equation here. It's your termination minus the characteristic impedance of the line divided by the sum of both. And so in the extreme, we talked about before, if your termination is zero impedance, you have a perfect short, your voltage reflection coefficient is -1, you get that voltage inversion. And in general, you get a voltage inversion anytime your termination is less than the characteristic impedance of the line, right? So I will say this looks more like a short. When this impedance is less than the characteristic impedance of your line. Looks more like a short, you get the voltage inversion, you get a nice current reflection without inversion. On the opposite end, let's say you have a perfect open for your termination, right? Infinite impedance, now this equation computes to a 1, and you get a perfect voltage reflection, but you get current inversion. And generally, that happens anytime you get this current inversion, anytime your termination is greater than your characteristic impedance. And I'll just say that looks more like an open, and we expect to see that current inversion. And so what are examples? So this is nice, but what are examples of terminations that we expect to see in a power system? Typical terminations. This would be a very typical one, right? We actually get a short circuit on the line. So that would fall under here. Fault, you'd get your, let me step back. Fault is when, that's a perfect example of a short. So we expect voltage inversion. Here's another type. Let's say you have a junction point, right? Where you have one line splitting off and another line splitting off at that junction point. This could be a substation, right? You have a line coming in, terminating in a substation. We have multiple lines leaving the substation. What does this characteristic impedance look like? Well, it's the parallel combination of those two lines, right? Or parallel combination of multiple lines. And so that is going to have an impedance that's less than the characteristic impedance of the line. So that's when you get that voltage inversion. So I put here junction or substation. Here, let's see that there. So how about current inversion? And open, shown here, you get perfect current inversion, right? And perfect voltage reflection without inversion. So we'll see that. Let's say we energize a line. Your end is open because the line was de-energized to start with. You energize the line, you'd expect to see perfect current inversion off the end of that line coming back at you. And we would do that when we're first trying to find the propagation delay of a line. You energize the line, you do that test, you actually see that bounce of the current off of the end of the line and come back. And then knowing that difference in time, you can calculate your propagation delay. And tapped transformers, we also expect to see that. That looks like a higher characteristic impedance than that of the line, so you also get that current inversion. So those are just some kind of typical examples that we'll see. Again, I'll just be referring to those as either looking more like a short or more like an open, just to keep it simple. So single-ended traveling wave fault locating is complicated, and I'm going to separate this. Ooh, don't do this too fast. I'm going to separate the types of reflections into what I call local reflections and then remote reflections. So here I'm showing just a simple two-terminal line. On my local end, I have a traveling wave fault locating relay installed, and I wanted to go over the theory going over voltages and currents. From here on the discussion, all we care about is currents, because at least the traveling wave fault locating relays I'm dealing with, which are those SCL411Ls, you just have currents, well, you have currents and voltages brought in, but your CCVTs and VTs have really bad characteristics for the high frequencies. They don't pass those very well, whereas your CTs do. So we're using CTs to look at this traveling wave phenomenon. And again, this is single-ended. We only have a traveling wave fault locating relay on this end, nothing on this end. And so when I talk about local reflections, we'll put a fault, and I'll be talking about the reflections going in between the fault and the local terminal. I'll go over later the remote end, which will be, because you're going to have reflections going in between here and propagating back through too. So let's just focus right now on just the local reflections. Get a fault on the line. We will get traveling wave voltage and current flowing back toward the local terminal. What polarities do we expect for these? I'm showing these correctly, but do these make sense? We get a negative voltage. It's depression in the waveform, right? We're collapsing the voltage at the point of the fault. So you expect that negative voltage polarity going to travel back. It's also going to have a negative voltage polarity travel to the remote end. Current, so current, you really, to solve this, you would look at what does this negative voltage look like subjected to that characteristic impedance of the line. But intuitively, this just makes sense. We have current, it's positive, it's flowing into the faults. Remember, I'm always defining current flow positive to the right. So our current is flowing to the right into the faults. Also makes sense. So those are traveling back to the local terminal. Now what happens? They meet this junction point, right? And this is going to be a substation with multiple lines or a transformer off of this. What does that characteristic impedance look like compared to the line? Is it higher or lower than the line? Lower, right? Because this is going to be a parallel combination of multiple lines. So it looks more like a short. We expect current to not invert, right? So the current stays the same. Voltage inverts. We're not going to care about voltage too much, but we'll throw it up there just to look at it. So the current's going to reflect nicely back. It's going to be less than this, but it's still going to reflect back at the same polarity. Again, we're really just focused on the polarities. Travels back to the faults. Again, another short condition, right? This is a perfect short, or maybe has some resistance, but it's going to be less than the impedance of the line. So we get another reflection back. No polarity change on the current. And it's going to flow back. And so the key thing here, because when you're looking at these single-ended events, you're going to be seeing all these little tick marks, and it's kind of madness to just try to parse out those tick marks. It really helps when you know what kind of polarities to expect off of those reflections. So this is a useful tool and kind of just keep in your back pocket. Remember, for local reflections, I see the current, same polarity. And so I can step through this again, and now it's just charting out this path that you see here. This is what you see on the Bewley lattice diagram, right? So now if we chart this path out with time in the horizontal axis, we get this nice Bewley lattice diagram structure starting to form. And we'll look at that in some other examples. So now what about the remote reflections? So that's going to be bounces off the remote end coming back toward the relay. So again, we place a fault, we launch waveforms going in both directions. Voltage makes sense. I have a negative polarity. It was a voltage depression, so it's going to put negative polarity going to both ends. Current, does this make sense? With positive current flowing into the faults. This current is negative because it's flowing to the left into the faults. Waveform's traveling to the right, but the current is flowing into the faults. Now, again, remote end. This is a substation with multiple junctions off of it. It's a lower impedance. We expect to not see any current inversion, just voltage inversion. So that current comes back, nice off of the remote end. Now we come to the faults, and we would expect part of the current to reflect back. Part of it may travel through that fault. If that's a perfect short, and we're just looking at a very simple circuit, and it's a perfect short, we wouldn't get any energy passing through that fault. If, though, this has some impedance, which almost any fault I've seen, especially ground faults, have some impedance associated with it. Plus, if you look at the multi-phase coupling of the lines, your A and B phase and C phase are all coupled with each other, and whatever phenomenon happens on A phase, you're going to see show up on B and C phase. So if you take all that into consideration, you're going to have some energy going through that fault. And so it passes through. There's never a polarity change when you're just passing through an impedance like that, only when you're looking at reflections. And so that returns back to the remote end. And again, now here the takeaway is opposite polarity. Remote reflections, opposite polarity. The local reflections were the same polarity, and we're just focusing on current here. So this will help us when we're looking at events later on. Do you guys have any questions so far? So let's now let's start to put this together to see what this would look like in an actual event. So I'm going to see what does this look like if we have a fault on 1/3 of the line, so it's on the first half of the line. What does that look like in terms of the reflections? So I'm putting my 3 points of interest being the local terminal, fault location, remote end, and now we're taking advantage of that Bewley lattice diagram. We're going to chart the path that these waveforms take with time in the vertical axis. And so your waveforms that would launch would go toward the local terminal and toward the remote end. Get a bounce off of the local end. Now we meet the remote end here. You're going to get a bounce back and a bounce back from here. And it continues on. And then finally that remote end propagates through. So this is what's going to happen, very simplified. We're not looking at any other reflections from other sources. It's just clean, perfect example here. What are we interested in when we're doing a single-ended fault location? We want to know that distance, right? From the local terminal to the faults. But we can see visually that that aligns with these 2 points represented here. So this would be your first traveling wave to arrive. This would be the second traveling wave to arrive. And this is a round trip travel. So we know that the time here is proportional to actually twice the distance since it's round trip. And so when you pull up if the world were perfect, you pull up a single-ended traveling wave event, you can see, hey, here's my first waveform to arrive, second waveform to arrive, calculate the fault, the distance to the fault, no problem. We'll see it's not all that simple and friendly, but that's the theory there. That's the perfect world. What do we expect in the perfect world for a fault on the second half of the line? So now we're looking at 2 different points here. Let's just follow this, how the wave propagates. Just play through the event there. Get the same bounces as before. Now we're getting this remote end reflection is going to propagate through that fault with this dashed line. And then subsequent reflections there. So now, again, our traveling wave fault location relay, it's recorded its first waveform to arrive, second waveform to arrive. This second waveform to arrive now was the bounce off of the remote ends, right? So now we are interested in this distance between the remote end and the faults. And we can see visually that aligns with that point on the Bewley lattice and follow it back to where the relay is recording. So again, it's proportional twice the distance, but now we're looking at, now your fault location, you look at those first 2 bounces, your fault location is going to be given with respect to the remote end and not your local end. And we will look at the polarities. We know this polarity will be opposite this, right? Because it's a remote end reflection, whereas before the polarity should be the same. So that'll help us in the event analysis.
So Robbie, this is single end analysis.
Yeah, exactly. Yeah, I'll do a little bit on the double end, but the single end is where all the headaches come in. And so here's an example of one of our lines that we installed this on. This is the Humboldt Trinity 115 kV line. You can see here it's about 70-mile line. And so we installed the relay at the Trinity end. And so I'll step through an example of what, this is the actual record that you would find. So you can already see that this is not the most beautiful waveform in the world. I mean, where are our reflections? Where's the interesting information in this, right? So you kind of first have to get a feel, this isn't shown very well, but you have time in microseconds shown down here. You have to already for single-ended method, you really have to have an idea of what you're expecting. It's really best to do a traditional fault location or just look at the relay. The relay is saying it's 20 miles down the line. That's kind of your starting point. So I would know ahead of time, well, what does 20 miles look like? Oh, it's around here. Well, that looks pretty significant to me. Not this. But you will see a lot of noise in your waveform, and it all depends on where the reflections are coming from. You could have reflections coming from behind you, right? It's bouncing off of transformers or distribution feeders coming in. You have ringing on the CT, and sometimes that shows up at the very beginning when you have this first impulse. This is the traveling wave that arrived from the faults. You get all this ringing showing up, bounces along the CT lead lengths. So it just takes some time to kind of try to put this together. But going through this example, well, let me point out here. So this whole timeline, what we're looking at here, this is 1/16 of a cycle, right? And the relay is filtered out all the 60 hertz anyway. You would see a little bit of a rise in this if it was actually, if they hadn't filtered out the 60 hertz. So all the action in a traveling wave event is not happening on a power system cycle like we're used to looking at. This is happening in 1/16 of a cycle for this 70-mile long line. It's a shorter line, all the action is going to happen in maybe a 32nd of a cycle or 64.
So that's current on the west.
And yeah, yes. So this is current on the vertical axis, and you can see kind of this is 314.4 milliseconds, 314.6 milliseconds. And this is 140 amps, 0 amps. So you get a pretty good spike. This is an actual fault event. So fault hits the line. After some time delay, boom, you capture it at the location of the relay. So that's this first big jump. And we notice this is positive polarity. So what's our next point of interest? Again, you're going to be using your traditional fault location techniques to kind of point you to where you should be looking. Matter of fact, for this one, pointed us to right here, which does look like a significant event. And we note from this is a negative polarity step change now, right? So is this going to be a local reflection or a remote reflection?
No.
It's off the remote end, right? So now well, I answered that question. That's a remote reflection. And so let's now look at I'm zooming in now on this event, just looking at those two key points. Let's look at the time difference between them. It's 253.4 microseconds. And so we know that propagation delay, that corresponds to twice the distance between the fault and the remote end. Right, so here's our distance equation. You plug in your relative speed of light factor. For this line, we would energize the line and we would actually figure out, looking at the reflection off the remote end, what this relative speed of light factor is for this line. It came out to, for this 115 kV line, it was 0.982. And so you multiply that by your actual speed of light in miles per second, multiply it by your time, and you divide by 2 because, again, that's the round trip travel between the fault and the remote end. And we get 23.2 miles. So our fault location estimate we put out there is 23.2 miles from Humboldt, which is the remote end. And we got field reports back, actual location, 23.5 miles from Humboldt. Now for most fault locations, for me, especially single line to ground fault, that is awesome, 0.3 miles. For traveling wave, that's actually not all that great. They promise to be, within like 0.1 miles, usually they say in general like one span length. So with this very simplistic calculation, I have not taken into consideration like your CT lead length, which we'll talk about later, maybe some other errors. But you can see even with just a very simple calculation, you get within 0.3 miles on a 70-mile long line. And there's a lot of different ways of looking at where do these points come from. Here, I'm always going to consistently look at the takeoff point here. The manufacturers, Schweitzer Engineering, they have their own methods. You can pull up different filtered waveforms and start looking at peaks. There's different tools out there, but just a very simple view of looking at it from the takeoff point is what I'll consistently use in this presentation. And so there's going to be a local reflection too, right? We saw in the Bewley lattice diagram. You're going to first see that remote reflection, but you're going to see local reflections too. Where does that happen? Well, for this event, this is the point of interest, and you probably wouldn't be able to spot that just blindly looking at the event, right? So you can see, I mean, this is a muddy picture. This is not easy. You're going to want to go after that first reflection point, which can be the remote end, like in this case. And even then, sometimes it can be really difficult. Sometimes that might be buried in some noise. And at that point, you might want to pull up the Bewley lattice diagram and look at subsequent reflections, not just the first, but later reflections. So you can see it's a little bit challenging. So look at time. You know what? I'm going to skip this line energization part. I'm going to skip through this because we're running a little short. Okay. Back up a little bit. Okay, so for lines with complex topologies, let's see what that looks like. I just introduced a 1 mile tap in the middle of the line just to look at a simple case. For this, I'm going to split the Bewley lattice diagram up into 3 different sections. So we're interested in what happens in this portion of the line. This is showing what happens along the tap, and then this is showing the second half of the line. So what happens if you have a fault on a complex topology like this? We're going to put a fault location down at the remote end, see what happens. So these are the reflections, and these aren't all the reflections. These are just kind of some of the most significant ones. The traveling wave will hit the tap point here, and it'll start bouncing along the tap point, shown in green here, right? And these reflections will propagate back through the faults to the local terminal, shown here, red dashed line, yellow dashed line to correspond to these two. But you also get all these little reflections off of the tap that show up in this green. So now you're going to be looking at an event report here, and you're going to see all these bounces among many others, because you'll have reverse reflections happening, and again, I haven't even shown all of these reflections. So you can see it gets a little bit muddy. That's the point of interest. That distance corresponds to these 2 points here in time. And if you follow that all the way back to the source, that's what we're going to be interested in looking at the event, right? But you can see that this noise is going to be introduced into the picture. So just with a simple one-tap example, you can see that there's a lot of noise we're going to have to deal with. So this is one of the more interesting lines we have. We installed one of these on. We've got a couple of years of experience with it, so quite a number of events. This is the Bridgeville-Garberville 60 kV line. So your two transmission sources are Bridgeville, Garberville, and then you have these two tap substations. And it's all drawn pretty roughly to scale, but you can see this is about 19 miles, 4 mile tap, 8 mile tap. So this is going to get complicated, right? But let's step through some events to see what this looks like. So when we first installed this, we would pull up an event, traveling wave fault location event like this, and we'd sit there and scratch our head and say, okay, now what are we supposed to do with this? See noise here. We know this is the initial fault, right? This arrived back at the fault location relay at Bridgeville. But where's the fault in all this noise? Which is my point of interest? For this event, it happened to be this point right there. So I'll go through this event later, because actually we were able to provide a fault location for this. It's because operators took action to, once you energize the line, that's going to give a different characteristic than the initial fault. And then also when you start sectionalizing the line, you get a cleaner picture. So we'll go through this event and see how that plays out. So just want to throw that out there, though. And so what are our sources of reflection on a line like this? So it's pretty much anytime you have a change in characteristic impedance on your line, right? So here's your first change in characteristic impedance. If you start at Bridgeville end, you have a characteristic impedance of line, boom, you have a junction point, two parallel lines. So that would look like half of the impedance of the line. That's definitely a change in characteristic impedance. Fruitland sub, you get a bank, has a higher characteristic impedance in the line, right? So that's a source. Fort Seward Junction, another change in characteristic impedance. Bank and Fort Seward sub, and then Garberville sub, which Garberville sub is it has multiple lines leading it. Actually, in this case, only one line, but has another bank, so it still looks like a lower characteristic impedance in the line. It could also be open, like on a line energization test, or testing into a fault manual test. Okay, so this is a line energization event. And it's interesting because with a line energization event, you know all these distances. You pull up GIS, you know all these distances, so you can start to map out where you expect to see reflection points.
You know what GIS stands for?
Oh, sorry. Yeah, so GIS, in PG&E we have a GIS system, a Geographic Information System, I'm assuming it stands for. So that's, it's basically a program that maps out all of our lines. You could drill down to looking at individual poles, and it's the basis for what we use to figure out the lengths between these points. So I could use that graphical system to know the distance between Bridgeville Sub and Fruitland Junction. And that's what we go to whenever we're doing fault location. We kind of know with our fault duty program what percentage of the line we expect the fault to be. Then we would go to GIS and we figure out, okay, what is the actual mileage, the distance from Bridgeville Sub to that fault location is, or what's the whole number. And so this line energization event, we know, let's look at the first point of interest. This is when we would close Bridgeville Sub to energize the line. Garberville would be open, right? And so this first spike represents the traveling wave you launch when you close that breaker. And it's the current traveling wave, right? It's about 140 amps there. And so that's our line energization. We get this ringing effect. You see that a lot on traveling wave events. It's that stuff going on the CT secondary. So it's just noise. We're not concerned about that. But we know we can map this out. We can calculate what does a distance look like in terms of time on this waveform. Lines up right with Fruitland Junction. So we get this reflection off Fruitland Junction. It looks more like a short, right? So we get another positive current reflection back. Fruitland Sub looks more like an open. So we get a negative current reflection coming back. Fort Seward Junction looks more like a short. This itty bitty little reflection, if you want to call it that. We know it's there because we know the line length, but otherwise you wouldn't be able to tell from just looking at it. Fort Seward Sub, again, we get that negative deflection, which we expect because that's a higher characteristic impedance. And Garberville Sub is open, so we expect that negative reflection off of Garberville. So you can map this all out, and it's kind of fun to do that because you feel really smart because you know all these distances and you can just map it out. It's another thing actually trying to find the faults where you have no idea where it is, and you're looking for this to tell you where it is. So let's look at some fault events. What we would expect in looking at a fault event, single-ended fault event, is for any faults on this first section, we would treat that just like a clean two-terminal transmission line, right? There are no taps in between. You would treat, this is your local terminal, Fruitland Junction is now your remote terminal, and it's the same analysis as you had before. Problem is when you go out past that first junction point, that's where you start to have problems. And so this next event that I'll show you is an actual fault right around here, right down on this Fruitland Junction tap. And so that's this one. And remember, this is the one that I showed initially where the fault location is buried somewhere in here. So let's see what this looks like as I step through the event. So what do we expect to see? We have a fault out here. We get traveling wave launch and arrives at Bridgeville Sub. That's this first inflection point, right? Where else can traveling waves propagate? Well, it can travel out toward Fort Seward Junction and come back. And that's this negative impulse you see here. Now what happened is it wasn't exactly an inversion. What happens is as the traveling wave is propagating down the tap, the current flow is into the faults, right? Now when it goes toward the right, which I just showed, I'll rewind that and show it again, but when it goes to the right, the traveling wave is flowing to the right. Which way is the current flowing? Back to the fault. So that's shown as a negative polarity because I want to keep everything consistent. Our relays are looking to the right. So everything to the right is positive from that relay's perspective. So you have to keep everything in reference to right is positive. So that's why you get this negative. And it bounces clean off of this. It looks more like a short, so there's no inversion, just stays negative and comes back. So I'll replay that again. Okay, that was the first one. We'll go to the second one. It's negative and it bounces clean right back to Bridgeville. What's another source? So you have it travel off to Fort Seward Sub. And off of Fort Seward, you had another inversion because it's a higher impedance. So it inverted again, now it's positive. You see that reflection point. And you get a reflection off Garberville. Garberville was closed because this happened when the line was just energized sitting there, and so you get a clean reflection back and it's negative. So what about the actual fault location, right? It's nice to map out these other points and reference them, but where is it actually bouncing off the fault? Fault going back to Bridgeville, back off the fault, back to Bridgeville sub. And that's this point here. This is our fault location we're interested in. So you wouldn't, I mean, if you have hours of time after the fact and you want to do a very accurate fault location, you might be able to piece all this together. You're not going to be doing this on the fly, at least I wasn't able to. But let's look at another event that might clean this picture up a little bit. So this is now the line, this was a sustained fault, and the line is tested into manually again. So here we're energizing the line now. So now the waveform, this first impulse, that is not created by the faults, that's created by line energization. And now we want to see the reflection off of that short-circuited fault. So the traveling wave goes down to Fruitland Junction. What we expect at Fruitland Junction is we'll see a reflection back off the junction, and we'll see part of it continuing on down to the faults. So you get that. That point arrives, that's your reflection off of Fruitland Junction, positive polarity. And then finally your reflection off the fault arrives. So this you might have a chance actually doing a fault location off of. I think you kind of got lucky with the relative position of where this is. If it were closer to Fruitland Junction, it'd be buried in this noise. Or if it were closer to the bank, you might get more noise on that side. So it's not a perfect picture, but in hindsight, we could say, yeah, that's where the fault is. Fortunately for this event, operators took further action and opened up this switch here by SCADA. So our operators from their office are able to open up the switch, test back into the line, make sure that the fault isn't on this section here. When they do that, energize the line. There we get our first impulse, line energization. Now when this arrives to Fruitland Junction, there is no junction point. This is going to continue right on down to the Fruitland sub without any reflection off the junction. And our first reflection is off the faults. So now we have a nice clean picture. This is the event you're going to be using to do your fault location, if you're lucky enough to have operators sectionalize your line and test.
So maybe you're gonna talk about this later, but I would assume Fruitland tap would be smaller conductor than Bridgeville.
Yeah, and I haven't seen,
You don't see much.
I don't see much effect in that. Yeah, your characteristic impedance, it's not going to change a whole lot from different conductor types that I've seen. But you definitely, anytime you have a junction point, now you got half of the characteristic impedance that you had before. So you definitely see those reflections.
That's what I was gonna say, is the impedance difference between two different wire sizes is relatively small compared to that.
That junction point.
Parallel of two impedances at that junction.
Right.
Apology, that's more.
Yeah.
If you hit
Definitely.
an end point that looks like an open, or you hit a junction or transformer, something like that, much more significant than just a conductor section.
So, and we could look at the time difference, and we can just use that same formula up here. Relative speed of light times your speed of light miles per second times time divided by 2, 20.27 miles. And using our GIS system I was talking about before, that corresponds to pole 1/8, and that's the fault location that we gave. Field report came back, tree removed between poles 1/8 and 1/9. So that was it's nice to give a perfect fault location for a little rinky-dink 60 kV line where you have a fault way out on a tap. Using conventional methods, I mean, I'd be happy to just tell them it's somewhere out on that tap, go look at it. Now I can give them the whole number. So when it works, it's awesome. But it doesn't always work. It's often very difficult to give these fault locations just using a single-ended method. So what about double-ended traveling wave fault locating? So this double-ended is awesome. You don't care about any of the stuff I just talked about. You don't care about the polarity. You don't care about reflections. You care about what time. You care about the timestamp of arrival for this first waveform. The timestamp of arrival for the local event capture. So you have traveling wave relays installed at both ends. This is connected to a very high accuracy GPS clock. This is connected to high accuracy GPS clock. They both record just that first impulse we saw on all those events. And that's all you need for double-ended method. There's your line length. It's a very simple formula that gives you the fault location. Basically, you need your T sub L, your T sub R, speed of light, plus the length of the line. And so that's going to spit out 5.2 miles, and you're done. And so the relays actually just calculate this. If they're connected through comms, they communicate that information to each other, and they report this number. If they weren't connected through comms, you could just pull up in the relay event files, the header files. It shows this arrival time both ends. Plug it into that simple formula, walk away, and you're done.
C is the propagation.
So yeah, I should have put CR times C actually. So this would be your actual miles per second adjusted by that factor.
So are there any cases where the traveling wave fault locator at the local versus the remote will have two disparate times? Meaning if I use a 0.985, if that's what I calculate after having closed the local end into a remote, an open remote, am I going to get that exact same time constant closing the remote into an open local?
You should get exactly the same time, yeah.
So when you guys are commissioning it, are you only just doing it from one end and applying that same constant in the both relays?
That's, yeah, exactly. And I mean, usually for us, especially like on a line like this, you have a bunch of taps. I can't get a clearance to de-energize the line, so I'm just mapping this into the relay. I'm mapping the breaker seal into the ER mask, capture an event on the line test, and usually we're just line testing from one end. So I usually just get that data on one end anyway. And I just assume it's going to be the same, yeah.
You could get a slight difference because we're correcting by that. We're lumping the current transformer secondary lead.
Yes.
And if one end is real short, one end is real long, that could give you a little difference. But again, that's typically going to be less than 1,000 feet of difference between the two.
Right.
Which is not many microseconds.
Yeah, and this formula does not accommodate for that CT lead length, but it'll give you close enough in most cases. And so what happens to the double-ended method when we have a tap down? So fault happens at t equals 0, right? These now, the waveforms arrive at, let's say, t tap. Now our time captured here is t sub r plus t tap. Ooh, this should be t sub l plus t tap. There we go. Just pretend that's an L. And so we plug that into our formula, so now it's T sub L plus T tap, T sub R plus T tap. These cancel out, right? So this, doing a double-ended method, everything's going to appear just to be right at the beginning of the tap. Doesn't matter where it happens along this line, your double-ended method is going to say it's right there. And you just have to know to interpret that, hey, it's telling me it's right at the tap. All I can tell from this double-ended method is to control the tap. You might then try to use your single-ended method if it works out for you, if they sectionalize and test it and it's a clean enough event, to actually give a better event. So your single-ended has at least the possibility of giving you more information than this double-ended method for taps. So results. So this is the Humboldt Trinity line. You know what? Let me zip through these because I'm just showing in detail. These are the results summarized. So this is our Humboldt Trinity line. You can read this. This is the estimated location field found results. This was our more complex 60 kV line. Estimated location field found results. I can just summarize it for you. We basically had one dead on in this, and we're off by 3 in our worst case.
And 3 poles of structures.
3 poles of structures, right? And for the Garberville line, we were dead on 3 out of 6 of them. And again, our worst case is that 3 structures we're off by. And so what you might notice, though, if you're looking at the data really carefully, we were always estimating too far. That was the one consistent thing. that's where your CT lead length comes into play, right? We were not accommodating for that line extension from the CT lead length. And CT lead length, I mean, you may say, I mean, what is that compared to the length of the line? It's not a big deal. But light is going to propagate down that CT lead length because it's covered by a dielectric and it's not air insulated like the primary. Your light is going to travel, I think they quote around 60 to 70% along the CT lead length. So your light is propagating a lot slower. Those CT lead lengths look a lot longer than they actually are.
Instead of 98, maybe 98.5%.
You're down at 0.6 something.
Yeah, you're down at 60% of speed of light because it's insulated CT secondary wire.
And so if your relay is located at a very big substation where the circuit breaker is almost not even visible off in the distance, that's going to really play into effect. And even here, so when I look at the offset, there was a net offset of 0.19 miles in this case, 0.06 miles in that case. If I accommodated for that, then my error would have only been about plus or minus 0.06 miles or 300 feet for these cases. So if you accommodate for the lead length, you can get your accuracy down to being, you know, one span really, we're looking at. So you spent a little bit of time, so I'll talk about, what about other effects like change in elevation? This is our Humboldt Trinity line, and I'm mapping out showing each structure here, and this is the elevation in feet. So this is 0 feet sea level. This is almost a mile up. You can see this, I mean, you have quite a bit of elevation change throughout this profile, right? So the total line length is about 70 miles. The cumulative change in elevation, if I add up all this elevation change, that adds up to 7.6 miles. So you would think this is, I mean, this is going to introduce massive error. If we take this simple, I mean, let's look back to the basics though. If we're considering B is the length of our line and A is the elevation change, what we're actually looking at is C, right? And if you take that into consideration, now the elevation really only adds 0.67 miles to your total line length. It's still 0.67 miles. Thing is, when you test your line, this 0.67 miles, you're going to test your line, see what the propagation is like along that line. You're just going to get a lower speed of light constant factor. So instead of 0.98, maybe the effects of this is going to make it look like a 0.976, something like that. So it just gets absorbed into your relative speed of light factor. That's assuming that this is relatively constant over the whole length of the line. If you have extremely mountainous terrain, then you go to flat valley for a long amount of the line, all that error is right up front on your line. That's going to play into it quite a bit. So we looked at it for this, this was set there. We looked at it for this line. We take an elevation model, and then we take a flat earth model. And let's just compare structures at each point along this model and see where our biggest discrepancy is. So for this line, it happened to be our 265th structure. That resulted in the largest discrepancy between these 2 points here. And so that worst case was only about 0.04 miles. So even with that profile, it's pretty uneven, you can see, but it's not, you don't have it all concentrated in one section of the line. It's still only 0.04 miles is your worst error that's going to result in.
This is something that's brand new for us, so we were concerned that, hey, is this a big source of error? And you can tell that after running all these calculations, we determined it's really a very, very minor amount of error.
That's the same as SAG. Current distance between point A and point B versus.
Yeah, exactly, right. So your sag is going to also, I would expect that to be pretty evenly spread over the length of the line. So that'll just get absorbed into your relative speed of light constant.
And none of us really think that the Earth is flat, but that's the way our GIS system is set up. It's kind of based on a flat plane model.
And by the way, I mean, there is, if this is going to be a problem on one of your lines, there's a website where it's a federal government website. You can enter coordinates in a spreadsheet, spit it into their website. They feed back the elevation at each point. Then you can just use a spreadsheet to calculate basically what I did here. So you can create an elevation model pretty easily if it was problematic.
What we discovered is why bother because it's such a minor.
0.04 miles for that 70-mile line. And so here I'm just going over some other correction factors. We talked about CT lead length, line modeling errors. Of course, that's going to get you if your GIS is off. Conductor sag, we've talked about that right now. Elevation changes. Most of these are really just factored into your relative speed of light constant. Unless it's really inconsistent in any parts, if it's evenly spread over the length of the line, we didn't see any reason to really worry about it. And so conclusion, single-ended traveling wave fault locating is complicated, especially when you compare it with a double-ended method. You're just taking two timestamps and plugging it into a very simple formula. Single-ended fault locating, I mean, looks like very complicated forensics at that point. It can be simple, but it can definitely lead to head scratchers, especially when we're talking about these complex line topologies. But if it works for you, it can be extremely accurate. And like I said, it's pretty awesome giving with confidence a fault location out on a 60 kV tap, knowing you got to go right to that structure plus or minus one structure. Requires training, definitely. You're going to have to look through a lot of these events before you start to get comfortable with it, or at least I did. Requires new software. So there's the new SCL Synchrowave software. You can plot out these Bewley lattice diagrams, and all these events are shown using that software. And TWFL on complex lines definitely has gaps. And it has gaps for both the double-ended method and the single-ended method, right? The double-ended method, you cannot give a fault location out on the tab. You can just say it is on that tab. Questions?
So one thing I don't think we did a great job of is, why do we care about these fault locations? What's the benefit to the utility? So there's a couple different benefits. One is if it's a sustained fault, the faster we can get people out to the site to identify the problem, clear it, repair it, the faster we get our customers back. The other aspect is that if it is a momentary fault, say we get a lightning strike and it cracks some insulators, but the line tests okay, so it's, the customers are back, but if we can't tell them pretty precisely where to go look for trouble, they may not find it. So that may mean that the next time it rains or something happens, we may get another fault in the same location. So we're trying to prevent subsequent faults due to that damage. And some of these lines, it is 67 miles, you can see there's a lot of elevation change. Some of these are very hard to drive to, especially if it's wet and muddy or if there's snow on the ground. And so a lot of our patrols are done with helicopters. Helicopters cost us about $1,000 an hour, plus the cost of the people that are sitting in the helicopter to inspect the line. So if we can reduce that time, it's a lot of money savings for our customers. So fault location is very important to utilities, and so that's why we're spending this kind of effort to learn these new methods.
So compared to previous methods that you've been using, is this by far the most accurate method?
I'd say, well, it's definitely the most accurate, and for me, even more importantly, it's like a 0 or a 1. You have a lot of confidence when you actually find a fault location, when it's clear on the record that that's where it is. You have very high confidence that this could be a location. I mean, when we give out fault locations for clean lines like the Humboldt Trinity line, we do often get pretty close, but we're not always sure of that. I mean, we could easily be off by 2 miles, and maybe we're there within 0.2 miles. But
impedance-based methods, which where you're just
right
from the relative ohms from each of the line. The relays do some magic, and we do some magic, trying to come up with the best estimate. We've been doing that for quite a few years at PG&E because we tend to have messy lower voltage transmission lines. We average over many years, average less than a mile of error on average. And I think in the last year, we've gotten down to less than a half a mile of error. But occasionally we'll run into one that's a high impedance ground fault that you'll be 10 miles off. So our average is pretty good, but there are a few exceptions. And so like Robbie said, when you have confidence in this data, you can always get within one structure. So for our line guys out there, especially if there's 10 feet of snow on the ground, which we have locations where we get that, this can be extremely important.
And how much costs for the fault relay?
These relays are costing per Per relay, I think they're between, well, the way we configure them, between $8,000 and maybe $12,000 per relay.
And this feature was like a $1,500 adder?
I think it's $1,450 per relay to add this, but we talked them down into a pretty good discount.
And how long have you been using this method? Your experience goes back to.
So for just this relay, probably 2 years, 2.5 years.
Yeah.
We first bought 4 as kind of experimental. And Robbie put in two of the 4 relays, and now you've got 3 of those for 4 relays. But this is our standard relay for all of our lines for the last probably 3 years, 3.5 years. But initially we decided not to pay for this extra adder for the traveling wave option because it was an extra cost. But since we've started to get this experience, we've changed our mind and we're now getting that option for, I'd say, almost all of the new relays we order.
So I know that there are a lot of PMU installations, or at least there was a lot of talk about PMU installations in PG&E system, and since everything is time-stamped using the PMU, has there been any analytics implemented in PMUs to go and do the same?
I'm not aware that we've ever really looked at that in PMUs.
I think
Well, and-
PMUs only update once per cycle.
That's right, it's doing it a
It's a
definite
pretty slow.
time, it's not capturing this, because this thing's running at, what is it, 3 megahertz sampling rate or something?
It's 5 megahertz.
This is more of a transient device rather than a disturbance
Right.
device. Yeah.
So a fault.
Well, the time-stamp on PMU can be really short.
Sure.
Like,
Mhm.
it's, I don't have a good number in my head, but comparing to RTU devices, it's a lot shorter.
But I think
So-
they're only sending that data
Sample.
like once a second because of the vast volume of data you generate.
The time accuracy requirements are pretty much the same. They're
Yeah.
very high accuracy, it's like 200 nanoseconds, I think is what's preferred.
Mhm.
But this is capturing about half of a cycle right at the fault incident. The T400L relays, they're capturing, I think, like a second and a half or longer, so you get that full picture. But yeah, the PMUs, they're just capturing at definite timestamps, and it's not going to correlate to the fault event.
So we've done several different vintages of traveling wave. They require high sample rates, pretty good processor speed, and probably most especially highly accurate clocks. So 10 to 15 years ago, the satellite clocks that we were using were called GOES clocks, GOES, which was a US government time signal. It was not as accurate. We used that and a single set of potential transformers on a bus to look at all the lines connected to that station. Basically built our own system of traveling wave fault location. It was not that accurate. It was somewhat limited by the clocks available at the time. And you weren't looking at data on a single transmission line, but all of the lines connected to that bus were coming into one device, and all you got was a timestamp. You didn't get any of the Beauty lattice diagram. You didn't get to see the deflections of the traveling wave. All you got was a timestamp. So we kind of abandoned that system after a while, and for the last maybe 14 years, only on our 500 kV system, we've used another commercial product, which is a standalone traveling fault locating device. So it'll do all the lines into one box, but you're paying several $1,000s for a box that all it does is give you this timestamp data for the lines in that station. And then you have to have one of these boxes at each end of every line to do this. So this is the first relay that really provides this inside of a line protection device. So they're not cheap, but we were already buying these relays. So we were only looking at the cost adder of about $1,400 per relay to upgrade our existing new relays we're putting in to get this function. And it's done in the relay device itself instead of a separate box.
Another question out of curiosity. So right now you're using the waveforms that already existed in the system because of the fault. So is there any way that you can do your own experiment with your own waveforms, maybe low voltage waveforms, but higher frequency using the same device, come up with a fault location?
So there are devices mostly for lower voltage systems. I did see some literature that was like handwritten in some ancient paper in one of our files one time. We actually did that on the 230 line out of Brighton Sub, which is right over here on the corner of Folsom Boulevard and Power Inn. We've got a big substation there. Back about 1970, if they had a line, one of the 230 kV lines that tripped and locked out, they'd send a communication tech out there with a variable frequency generator and an amplifier, and they would connect those temporary devices to the secondary of a voltage transformer. And then they would couple that up to the 230 kV line and vary the frequency and look at the waveform on an old-fashioned oscilloscope to try to determine, as they swept the frequency, change the frequency, how far out that fault was. I've never seen that. I read some documents that they were doing that back in the 70s, but I think that was kind of an R&D effort and not, obviously never was used beyond that one location. But yeah, lower voltage like telecommunication circuits, service wire to people's house, they do a thing they call a thumper. Uses some of those methods to try to locate underground faults because you can't see it. You don't want to dig up the entire length of a telecom circuit or an underground line to try to find where a fault is.
Is having a double-ended system more accurate than having a single-ended?
I wouldn't say it's more accurate. It should theoretically be the same accuracy. It's definitely more consistent. As long as your clocks are accurate, you don't lose accuracy on your clocks, you will get a double-ended fault location, except if you have taps, then you can't identify, you can only identify, hey, it's somewhere on the tap. But you'll always get a fault location, assuming your clocks are good. Single-ended method, it's a mixed bag. Sometimes you get it, sometimes you don't. But that's why I say this traveling wave fault locating, it's like a 0 or a 1. Either you get a result, whether it's single-ended or double-ended, you get a very good result, or you get nothing at all.
And then could you analyze, if you had a double-ended system, could you analyze 2 single-ended?
Yeah, definitely, right. Especially if it's out on that tap, it'd be worth looking, basically doing the single-ended method that we looked at from both ends. And one end might give you better results than the other. Yeah.
Still couldn't tell where it was on the tap.
You possibly could. Even if it's a clean tap, you could possibly tell along the tap where it is. Definitely with a line test, it's a lot easier, but yeah, it's possible.